Hi there, today's paper is AQA AS Physics Paper 1 from 2020. So the first question is some particle physics. We're given a strong interaction between two protons and we want to find the lepton number, the strangeness and the charge of this mystery particle X. So what we do is we just write down the lepton number, strangeness and charges just like balancing an equation. So first of all, what's the lepton number of a proton? Well, protons are not leptons. So the the lepton number of those is 0. They're baryons. The pions are also not leptons, they're mesons. So they also have a value of 0. And I'll write Lx for the lepton number of X. And if you solve that, you simply get Lx is 0. Strangeness next. Well, for a particle that has strangeness, it must contain strange quarks. And protons don't contain those, because a proton is 2 ups and a down. And pions are made from ups and anti-downs, or downs and anti-ups, or ups and anti-ups. Okay, but they don't contain strange quarks. If they did, if you did factor that into a meson, you'd end up with kaons, which is something different. So 0 plus 0 plus 0 plus the strangeness of X. So again, trivially, that's 0. And then the charge, Q, well, protons have a +1 charge. So let's write like that. And the charge on a pion is just is indicated on it. So a pi plus has a charge of +1, a pi minus has a charge of -1. So if we put all that together and solve it, we get that the charge of X must be +1. So what is particle X then? Well, it's not a lepton. It doesn't have any strange quarks, and it has a charge of +1. So what must it be? Well, it must be a proton then. Why not a pi plus? Okay, because the baryon number is not conserved there. Okay, so it must be a proton. And third part, we're told a pion can decay into an electron plus something else. So what's the other particle? Well, do the same sort of things again, balance values. So let's balance, the charge is balanced. If the charge is balanced if it has a charge of 0. If we look at the lepton number, we get 0 equals 1 plus the lepton number of Y. So that tells us that the lepton number of Y must be -1. So it's an anti-lepton. So this is enough information to then make the right choice. So it has to be an anti-lepton which doesn't have any charge. So that must be just the first one. In fact, in this case, there was no point checking the charge because all of the particles that are given are chargeless. 1.4. Some subatomic particles are classified as hadrons. There are 2 classes of hadrons. Discuss the nature of hadrons, and your answer should include these following bullet points. So here's a big 6 marker. So what do we know about hadrons? Well, first of all, the basic thing about hadrons is they are made of quarks. Okay, and there's 2 main families. There are mesons and there are baryons. Mesons are made of 1 quark and 1 anti-quark. Baryons are made of 3 quarks. So, e.g., up, up, down, and for this one it could be up, anti-up. Okay, up, up, down would be a proton, up and anti-up would be a pi 0. Okay, so we've done, what else can we say about hadrons? Because they contain quarks, they interact via a strong force, strong interaction. Okay, so I think we've done that, and we've done that. Last bit, a discussion of the stability of free hadrons. So let's just say a little bit about that. So this is just a fact you should know. The only stable baryon is the proton. So anything else, so say a neutron, so you might give an example of a neutron decaying. It could decay into a proton plus an electron plus antineutrino. Okay, and that's what we've got there. Right, question 2, a bit of mechanics now. So we've got a spacecraft entering the atmosphere of Mars, and it must decelerate to land undamaged on the surface. Figure 1 shows the spacecraft of total mass 610 kilograms entering the atmosphere at 5.5 kilometers per second. Calculate the kinetic energy. So half mv squared for kinetic energy. So we've got half 610, and we're a little bit careful before is that you convert the speed into meters per second. So 5.5 times 10 to the 3 meters per second, and that's squared, of course. So if you put that all together, you get 9.2 times 10 to the 9 joules. And I've chosen two significant figures because my question, the data in the question, the lowest number of significant figures is 2. So that's why I should give in the answer. Okay, or you might write this as 9.2 gigajoules if you wanted to. Okay, so next we're told that the parachute opens on the spacecraft to slow its descent. And we're showing that some gas is being displaced that way, and there'll be other directions as well. And we need to explain, with reference to Newton's laws of motion, why displacing the gas causes a force on the system, and why does this force cause the system to decelerate. Okay, so first of all, if the gas is displaced, then its momentum is changing. Okay, and therefore the gas feels a force from the parachute. And you need to refer to Newton's laws of motion, so this is where you can say that you can put an equation in, so F is equal to delta mv over delta t. Okay, because its momentum, the gas's momentum has changed with time, it must be because it has experienced a force. So this is Newton's second law. A bit of a generalization of F equals ma. So if the gas feels a force from the parachute, then the parachute experiences an equal but opposite force from the gas. And that, of course, is Newton's third law, equal and opposite forces. Okay, so there must be a resultant force which acts back against the motion like this. So the gas has been displaced in lots of different directions, but overall the gas is being displaced in the direction the spacecraft is moving. So the force that the gas puts back on the parachute must be in the opposite direction to which it's moving. So parachute experiences a resistive force opposite to its motion. So opposite to the direction of motion. And you're asked to explain why it decelerates, so it's important to say that this is which is larger than the weight acting down. Okay, so because the force acting back is greater than the weight acting down, therefore resultant force is opposite to motion, therefore deceleration. Okay, so now having explained why it decelerates, we have to do a calculation. So we're told that the system falls a distance 49 meters, loses a certain amount of kinetic energy. Obviously it's losing kinetic energy because it's slowing down. And also a certain amount of energy is being transferred to the atmosphere. So this is telling you this bit that work is being done on the system. So calculate the acceleration due to gravity as it falls through this distance. Let's just draw a little picture first, a free body diagram. So we've got this object that's fallen. It has a weight mg. It experiences a resistive force F acting up, and it's decelerating as a result. So let's put the acceleration point up here that we need to find. So we've got F minus mg is equal to ma. So the acceleration due to gravity that we want to find, if we rearrange that, that's going to be F minus ma divided by m. So what I need to find is I need to find F and I need to find a. Well, F I can find from the work done. I know that the work done is equal to F times S. Okay, the force acting over it, over the distance it's traveling through. So F is equal to work done over S. So that's 3.3 times 10 to the 5 joules of work as it falls 49 meters. So that's 6,735 newtons if I work that out. Acceleration, well, what do I know? I don't know a lot here, but I do know that it's losing energy, so its speed's changing. So I'm going to use this one. V squared equals u squared plus 2 equals u squared plus 2as, because I know the distance it's fallen and I'm looking for the acceleration. But I don't know v and u. But if I rearrange this like so, v squared minus u squared, that sort of looks like kinetic energy, except I'm missing a half m. So if I multiply the top and bottom both by a half m, I get a half mv squared minus a half mu squared divided by, well, the half and the 2 on the bottom will cancel and I'll just have ms on the bottom. But what's this on the top? Well, that's the change in kinetic energy. So I've got 2.2 times 10 to the 5 divided by 610 times 49, and that gives me 7.36 meters per second squared. So if I put all that back in, I've got 6,735 minus 610 times 7.36 divided by 610. And that gives a value for G on Mars of 3.68 meters per second squared. Or 3.7 if you want to go to the right number, sig figs. Okay, dust from the surface of Mars can enter the atmosphere, which increases the density significantly. Deduce how an increase in dust contents will affect the deceleration of the system. Okay, so more dust means there's more gas to displace, or more dust to displace, more mass to displace, however you want to write that. So that means there's going to be, if there's more mass, then there's going to be a bigger change in momentum. The change in momentum was proportional to the force, so there's a bigger force acting back on the parachute. And if there's a bigger force on the parachute, then the weight hasn't changed, the weight of the spacecraft hasn't changed, so if there's a bigger force acting backwards, then that's going to cause a bigger resultant force backwards, so a bigger deceleration. Right, some more mechanics now. So we've got a golf ball being putted along to the hole, goes 1.3 meters, and we're told that initial velocity is 1.8 meters per second, and we want to find the speed just as it reaches the edge of the hole, the velocity rather. So what equation should we use here? We know V. We've got we're trying to find V. We've got U. We've got the acceleration or deceleration, and we've got a distance. So we're going to use this equation again. So V is going to be equal to the square root of U squared plus 2AS. So just put all the values in. So it's 1.8 squared plus 2 times 1.2 times 1.3. And if you put all that together, you get 0.35 meters per second. Okay, so the golfer ends up in the bunker, the sand pit, and the golfer then hits the ball to get it out, giving it an initial velocity u at an angle of 35 degrees above the horizontal. And we're told that the horizontal component of u is 8.8. Let's just draw a vector diagram here. So we've got u, that's the velocity. This is 35 degrees. So this side is u cos 35, and we're told that that is equal to 8.8. And we need to find the vertical component, which is u sine 35. So how do we go about doing that? Well, let's call this a different symbol. Let's call this u that we're trying to find, the vertical component. So if I do the vertical component divided by the horizontal component, then that's going to be u sine 35 over u cos 35. So why have I decided to divide? Well, the whole reason for doing that is so that the u's will cancel out. That's the reason for dividing. It's not just some guess that it would work. The u's will cancel. And sine over cos is tangent. So what we get is that u, the vertical component that we're looking for, is equal to 8.8 tan 35. And that gives about 6.16. Now, whenever you're asked questions like this on the physics exams, approximately, you cannot just write 6 as your answer. You have to show that it gives an answer of about 6, so that you can say, well, that's approximately 6 then. Okay, there's always one mark for showing your approximate answer before then putting the final answer. So when it reaches X, when it's out of the bunker, out of the sand pit, it's moving horizontally. So that means that the vertical component is now 0. And that's let's call that V. So the vertical component of the final velocity is 0. Calculate the time taken. So we know the initial velocity up. We just worked that out. That was 6.16 meters per second. We've got that acceleration is, well, if we're taking that as 6.16 positive, then acceleration acting down is minus 9.81. And we know that v vertically is 0. And we want to find the time. So let's use v equals u plus at. So t is equal to, if we rearrange that, v minus u over a. So we've got 0 minus 6.16 divided by minus 9.81. So the minus signs cancel and we get 0.63 seconds. And just always when you're doing questions like this, just say, does that seem reasonable, a ball being hit out of a sandpit? Yeah, less than a second, that seems like a reasonable answer. Okay, how high has it travelled to get out of that sandpit? Okay, so we're looking for S this time. And remember, we knew V, we knew U, we knew A. So what's the equation that links those? V squared equals U squared plus 2AS. So if we rearrange for S, we've got V squared minus U squared over 2A. So 0 minus 6.16 squared divided by 2 times minus 9.81. And that gives about 1.93 meters. Right. So the golfer puts it back where it was, has another go. He wants to practice his shots and he wants it to get to X but with a smaller horizontal velocity. So how can he do that? Well, what the golfer should do is just hit a shot that goes up like this instead, much higher to that point. So that's 3.5, sketch the possible trajectory, a much higher parabola. And 3.6 is explain your reasoning for that. There's various ways to explain it, but the simplest way is that the ball travels higher, so that means it has more time in the air. And horizontally, we just got S equals ut. This would usually be plus a half at squared, but there's no horizontal acceleration. So S equals ut, which is just distance equals speed times time. So if t is greater, then u must be lower for the same displacement, same horizontal displacement. Okay, and that's enough to explain it. Okay, if it spends more time in the air, then it must be going slower to travel the same distance in that longer time. Right, question 4, sort of back to particles now. So we're told a sample of pure boron contains only isotope X and isotope Y. A nucleus of X has more mass than a nucleus of Y. The sample is ionized, producing ions each with a charge of plus 1.6 times 10 to the minus 19 coulombs. And the specific charge of an ion of X is 8.7 times 10 to the 6 coulombs per kilogram. Calculate the mass. Okay, this term here, specific charge, what does that mean? Specific is just a physicist's way of saying per unit mass. So if you have specific heat capacity as well, which you'll come across or may have come across already, which is the heat capacity per kilogram. So that's what specific means. So knowing that, if we remember that's what specific means, we can just say that specific charge is equal to the charge divided by the mass. So that's going to be useful to us. So we'll say that the mass is equal to, if we rearrange that, the charge divided by the specific charge, which I'll just call SC here. So the charge is 1.6 times 10 to the minus 19. The specific charge is 8.7 times 10 to the 6. So if you divide one by the other, you get 1.84 times 10 to the 26 kilograms. And we know that protons and neutrons are on the scale of 10 to the minus 27, so that tells us this is a reasonable answer. 4.2, determine the number of nucleons in the nucleus of X. So take that number that we just had, 1.84 times 10 to the minus 26, and divide that by the mass of a single nucleon, so that's a proton or a neutron. And if you do that, you get 10.8. Now you can't have a fractional number of nucleons, so let's just round that to the nearest number, so 11. Okay, 4.3, we're asked to compare the nuclear compositions of X and Y now. Well, what were we told in the question? X and Y are isotopes. Okay, they're isotopes of boron. So therefore, the proton number, the atomic number, is the same. So proton number is the identical. Same number of protons. But we were also told that X has more mass than Y. So therefore it must have more nucleons overall. And since nucleons is the sum of protons plus neutrons, and the protons hasn't changed between the two isotopes, then X must have more neutrons. Okay, and that's all we can see at this stage. 4.4 is what about this the specific charge? Okay, well, if X has more mass, and the specific charge was the charge divided by the mass, and we're also told that the ions have the same charge, so Q is not changing, then what we can say is that the specific charge of X must be less than the specific charge of Y. .5, we've got some values now. So table 1 contains some data about 2 completely ionized samples of pure boron. Each sample contains only isotopes X and Y. Deduce which sample, 1 or 2, contains a greater percentage of isotope Y. Well, first of all, let's just look at this column here, the number of ions in the sample. We can see that this the first sample has 10 to the 9 times as much. So just to compare, let's multiply the mass of the second sample by 10 to the 9 as well. So if we add 6.20 times 10 to the 10, then we can make a much more direct comparison. We can say that now, because we've multiplied the second row by 10 to the 9, the same number of ions has less mass. In 2 than 1. And therefore 2 must contain a greater percentage of Y since we said earlier that y was lighter than x. We said x had more mass than y previously. Right, onto some circuitry now. So a cell has an EMF of 1.5 volts and an internal resistance of 0.65 ohms and connected to a resistor R. Let's just draw a little picture in case that helps in the middle. So we've got a cell, 1.5, with an internal resistance, 0.65, and then it has a load resistance here of R that we don't know. So first question, state what is meant by an EMF of 1.5. So an EMF of 1.5 volts means it transfers 1.5 joules of, let's say, chemical energy to electrical energy for every coulomb of charge. Okay, and it doesn't necessarily need to be chemical. If it was a solar cell, it would be transferring light to electrical and so on, but let's just go with chemical here. The current in the circuit is 0.31 amps. Show that the total power output of the cell is approximately 0.47 watts. Okay, so this is hopefully quite an easy mark to get. So P equals VI. So 1.5 volts times 0.31 amps, and it gives 0.465 watts. Now this is another one where it has the word approximately in, so you need to go to at least one more significant figure than what it's asking you to find to show that it's approximately that. Calculate the energy dissipated per second, right? Energy per second, well, that's power. So what's the equation that we know for power? I squared R. But we don't know R. So how can we do this? Well, we can say that the power dissipated must be equal to the total power output minus the power lost in the cell. So the power dissipated through the internal resistance. So that's going to be, the total power was 0.465, and then we're going to subtract from that I squared times small r, so this is 0.31 amps squared multiplied by 0.65. And if we put that all together, we get 0.40 watts. Right, next part, the cell stores 14 kilojoules of energy when it is fully charged. The cell's EMF and internal resistance are constant as the cell is discharged. Calculate the maximum time during which the fully charged cell can deliver energy to the resistor R. Well, we know that energy equals power times time. So the total time must be equal to the total energy stored divided by the total power output. Okay, so we're not really interested in how much of that power is going to which resistor. All we're interested in is the total amount of power in the whole circuit. So we're going to have 14 kilojoules of energy divided by the total power, which was 0.465. Okay, so divide one by the other, and you get about 3 times 10 to the 4 seconds. Right, now a student comes along with 2 cells, and each of these cells has an EMF of 1.5 volts and an internal resistance of 0.65 ohms, so just like we just had. And they connect that to a lamp as shown here in parallel. The lamp is rated at 1.3 volts, 0.8 watts. So So deduce whether this circuit provides the lamp with the power it needs, 0.8 watts at that particular potential difference. So how do we go about this? Well, first of all, if we've got these values, we can work out the current required, which is going to be 0.8 divided by 1.3. So we've just rearranged P equals VI here. So we need 0.62 amps to be going through the lamp. So therefore I from each cell is just going to be half of that. So they each provide half the current. So that's 0.31 amps. So that's how much we need. So 0.31, 0.31. So what we can work out now is we can work out the volts that are lost in each cell. So that's just Ohm's law, IR, and R being the internal resistance. So that's 0.31 amps, which is flowing through the cell, multiplied by the resistance of the cell, 0.65, and that's about 0.2 volts. So therefore the terminal PD, what we're actually getting out of the cell, is 1.5, the EMF minus how much is lost, which is 1.3. And that's great because that's what we need. We need 1.3. So all good. 5.6. The lamp operates at normal brightness across a PD range 1.3 to 1.5 volts. State and explain how more of these cells can be added to the circuit to make the lamp light at normal brightness for a longer time. Okay, well, so more, should put more in parallel. So just add more and more cells in parallel. So that's the state part. Explain why that is the correct way to add them. Well, one way of saying it is that each cell is going to have to provide less energy every second or less power. Okay, or in other ways, you could say that each cell is therefore going to provide less current. And so if it's providing less current, then there's going to be less energy lost through the internal resistance. So there's various ways you could argue this, but this is probably the simplest that I've written here. Okay, last question now is all to do with stationary waves. So we've got a vibration generator on the left. We've got a piece of string stretched and then fixed onto another piece of apparatus at the other end. We're told that two markers, P and Q, are attached to the string and then some grids behind it so you can see what's going on. First of all, the string is made to vibrate at the second harmonic. Compare the motion of P with that of Q. So if it's the second harmonic, then that means if these are the two fixed ends, then the shape of the wave is like this. Okay, that's what the second harmonic looks like. If it's the nth harmonic, then we can draw it because it will have n+1 nodes. So one at either end and one bit in the middle. So P, marker P, is as far away from the vibration generator as Q is away from where it's fixed at the other end. So it doesn't really matter where it is, but as long as it's the same. So we can put one there and one there. So what we can see is that when P goes up, Q goes down, but we need to see it a bit better than that. So we can say that P and Q are in anti-phase with each other. Okay, that's the sort of term we should be using to describe that they're completely out of phase with each other. As one goes up, one goes down. And what we can also see is that P and Q must be, because they're the same distance away from the ends of the string, then the amplitude of those oscillations must be the same at each bit. So we've got these 2 points. So this is your answer really. P and Q are in antiphase and the amplitude is the same. Okay, now the frequency is increased. So we get this higher harmonic here. And it's showing that P and Q are now 0.55 meters apart. And we have to calculate the speed of the waves. Well, we know that wave speed is equal to the frequency times the wavelength. The frequency we're given, 250, that's being driven at. And the wavelength, well, what we can see is that from P to Q, we've got 2 full waves, because a wave is the distance from one point on the wave to the identical point on the next wave. So from P to this point in the middle here is 1 full wave, and then again to Q. So this is 2 lambda. So therefore lambda must be a half. The wavelength must be a half of that total distance. So put that all together and you get about 69 meters per second. Okay, so now we're asked about superposition of waves. So we've got these 2 waves which are superposing on top of each other to give the diagram that we just saw. So what properties must the wave have for this to be possible? Well, there's various things we can say. You don't need to say all of these, but they must be traveling at the same speed. They must have the same frequency, or the reciprocal of that, I suppose you could say, is the same period. They don't have to have the same amplitude, but they should have similar amplitudes. And the important thing, which I suppose you have to say, is that the waves have to be moving in opposite directions to each other. So one wave traveling right, one wave traveling to the left. So that when they meet in the middle, you get a stationary wave. Right, 6.4 is similar, but now you've got to draw it. So these 2 waves are coming together. Well, what you can see is that where there's a peak on one, there's a trough on the other one. Okay, and that's true all the way along. So in fact, if these add together mathematically, then the value is just 0 at every point. So hopefully you can draw a bit better than that and do it on the computer, but what you should have here is just a horizontal line basically. And then 6.5, annotate with an A the position of any antinodes. Well, there's always antinodes at either end. And these other points, which are never moving, so this one, this one, this one, these are going to be where the antinodes are. Okay, so they never move. So if I try and draw that on here, so there's 3 of those and they've got to be equally spaced. So there's one in the middle, and then one there, roughly. Okay, it doesn't need to be exact, but it needs to be close enough. Okay, and the last question on the paper now. We've got this picture of a vibration generator, and we're told that the frequency is reduced until the first harmonic is observed in the string, as shown in figure 13. The string is then, so while that vibration generator is set at that value, the string is then replaced with the one with 9 times the mass per unit length. Okay, so why are they telling me this information? Well, we know the fundamental frequency of the first harmonic frequency can be calculated using this equation: 1 over twice the length times the square root of the tension in the string divided by the mass. Okay, which anybody playing a string instrument should be familiar with. Okay, if we tighten the strings, the frequency goes up, it becomes higher pitched. If we've got heavier strings like the steel ones on a guitar compared to the nylon ones at the bottom, that makes it lower pitch. And if you shorten the length of the string, that again makes it higher. So you should be familiar with that maybe. Right. Now what we're doing here is we're replacing mu, the mass per unit length, by 9 mu. So that means that the frequency will become the new frequency 1 over 2L T over 9 mu, and we can take that square root because that's underneath the square root. Square root of 9 is like a third outside, so 1 over 3 multiplied by 1 over 2L T over mu. So a third of what we had originally. So this is the frequency of the first harmonic. However, the driving force that we set the vibration generator to is now 3 times the first harmonic frequency. Okay. So therefore, it must be the third harmonic, okay, which would look like third harmonic, 4 nodes, so it would look something like this instead. You might want to draw it on just to help with your answer. Okay, that's the paper finished then. So if you like that, please like that and subscribe to my channel. I also offer one-to-one tuition, so if you would like that, then please visit my website www.physicsmathstuition.com and I can help you out there. Okay, bye for now.